Welcome to the second part of the problem-solving session for Chapter 10. We begin where we left off, which is question 5. In the next 4 questions, we will be using the definitions of angular velocity, angular acceleration, the kinematic equations for constant acceleration, as well as the quantities that relate tangential velocities and accelerations to angular velocities and accelerations. So question 5 begins by asking, what is the angular speed of the minute hand of a clock? Well, what they are asking us to determine is what is omega. And they don't want the direction because they only want the speed. Now, omega is the speed of rotation. That's what is meant by angular speed. Okay? Tangential speed, so angular speed is omega. If we had been asked for tangential speed, that is v sub t. And let's not forget that v sub t is equal to r omega, so we would need to know how long is the minute hand to be able to say precisely what its tangential speed is, but we would have already had to calculate the angular speed. All right, so how do we calculate the angular speed? Well, we know that the delta theta of a complete rotation is 2 pi radian, and the time to complete a full rotation for the minute hand, 60 minutes, which is 3,600 seconds. See, it's in a sense the orbital period of chapter 6, if you recall, or chapter 13. So 2 pi is our delta theta, 3,600 is our capital T, our time to complete a full rotation, and so this gives us 1.75 e to the minus 3 radian. Let's write the proper unit. Radian per second. Okay, radian per second is the unit of angular speed. The next question asks us to determine the direction of the omega as a vector, the angular velocity now, if we are looking at the wall, if at the clock hanging on the wall. Well, let's see, if this is the hour hand and this is the minute hand, well, both rotate clockwise. And if we take our 4 fingers and we sweep them in the clockwise direction, notice that the thumb points into the plane of the clock, or in this case, into the plane of the board or the sheet, however we want to say it. So the direction of omega given by the right hand rule is into. Okay, part C says, what is the angular acceleration if the batteries are new? Well, that is, if the clock is operating as it should, there should be no angular acceleration because the hands should rotate at constant angular velocity. In other words, that the every second lasts as long as it's supposed to, every minute lasts as long as it's supposed to, and so does the hour. So these hands should be rotating at a constant rate, which means there should be no slowing down and no speeding up. Now the next part says the clock is now running slow. Well, that means that omega is decreasing, right? It's running slow. Its direction is still clockwise, so it's still into the plane of the clock, but because omega is decreasing now, alpha does not equal 0, since there is a slowing down that is occurring. But just as when we apply the brakes, if we are driving in the to the right, we apply the brakes, our acceleration is to the left. If we're driving to the left, we apply the brakes, the acceleration is to the right. So here the direction of alpha is out of the plane of the circle. So it's out of instead of into, as is the case for the angular acceleration. Okay, next problem. Question 6 states a discus thrower accelerates a discus from rest to a speed of 25 meters per second by whirling it around through 1.25 revolutions. Assume that the motion is circular with r, for example here, his r is the length of his arm, from here to here, is 1 meter. Now notice that here they've given us the tangential velocity, in fact tangential speed, not the angular speed, okay? Because at this position here, which is where the discus is 1 meter away from the axis of rotation, there is a tangential speed, v tangent, and let's say that this is the circle here. Omega would be, in this case, counterclockwise as he rotates down and up, but assuming that r is constant, so that the discus is always at the same distance from the center of rotation, which would be the axis about which the rotation is occurring. Anyhow, so let's write down the quantities that they've given us. Well, they've told us that this discus starts from rest, so essentially v from rest, v initial is 0. They've told us that at the point of release, which we're going to call v final, and it is tangential, by the way, is 25 meters per second. They've told us that the revolution, the number of revolutions made by the discus is 1.25, but revolution is not an SI unit, and therefore we must convert where 1 revolution is equal to 2 pi radian, and this gives us in fact, I just obtained the sum 5 pi over 2 radian. And another way that you can see this is 1 1/4 revolutions is 1 entire revolution, 2 pi, plus 1/4 of a revolution, which is pi over 2, and this is how I worked it out in my notes. And so 2 pi plus pi over 2 is 5 pi over 2. So they've told us that, and they've also told us that r is equal to 1 meter. The first question that they ask us to solve for is the arc length. Now, arc length is the length of the arc that is traced out by the discus. S is that length of the arc, and that is given by r d theta, where theta has to be expressed in radian when we use this relationship. Now we know that the length of the arm, or the distance to the center of rotation, is 1 meter, and we just worked out that the radian traced out is 5 pi over 2, so S is equal to 5 pi over 2 meters. What happened to the radian? Well, the radian, recall, is a dimensionless unit. Now, what in the world does that mean? Well, what it means is that although we understand that we are working with radian, this unit in itself, when multiplied by the SI unit, simply disappears. It's as though it has no dimension of length or no dimension of rotation. So if we want to express this in decimal form, 5 pi over 2 is roughly 7.85 meters. Okay, part B asks us to determine the angular velocity, or the angular speed, let's say, at the point of release. Well, at the point of release, we know, basically they're asking us for omega final, we know that v final is 25 meters per second, and we divide that by r because of the relationship that v tangential in this case it's the final, is equal to r omega. So this right here allows us to solve for the angular speed at the point of release. And 25 meters per second divided by 1 meter gives us 25. Now we're going to insert the rad. It's magically reappears in this case. Well, that's because when we express quantities such as delta, theta, omega, or alpha, we have to have the radian there to make sense of the fact that these are associated with rotations. Okay, the next question is, what is the centripetal acceleration of the discus? Well, just as in chapter 4, chapter 6, etc., it's the v squared, in this case the tangential, see, tangential divided by r, and that is 25 meters per second, the whole thing squared, divided by 1 meter. That gives us 625 meters per second squared. Okay, part D wants us to determine the angular acceleration. In other words, they want us to determine alpha. And here, although the definition for angular acceleration is A tangential over r, we don't know A tangential. That is an unknown, and so is alpha. We have two unknowns in the same equation. That's not good. How about this? Let's use the kinematic equations for constant acceleration. All right? Well, we know omega initial is equal to 0. We know omega final is equal to 25 rads per second. We know delta theta is 5 pi over 2. So we pick out the correct equation to determine alpha. And that would be omega final squared equals omega initial squared plus 2 alpha delta theta. That's 0. So alpha is equal to omega final squared over 2 delta theta. We plug in the values and we get an alpha which is equal to 1.59 radian per second squared. Now we can get the tangential acceleration, which is in fact the last part of the problem. The tangential acceleration is r times alpha. Well, r is still 1 meter, and since we now have a value for alpha, you can see that we can readily obtain the tangential acceleration of the discus as 1.59. Again, notice the rad will disappear, meters per second squared. Okay, next problem. The angular position of a swinging door is described by theta, by the way, that Q, theta as a function of time equal to 5 plus 10t plus 2t squared. And they want us to determine the angular position, angular speed, and the angular acceleration when t is equal to 0. Now, we have the position function, the angular position function, but before we can get the angular speed or the angular acceleration at t equals 0, we need to know their functional form. Well, the angular speed as a function of time is the derivative d theta dt, which is 10 plus 4t. Alpha as a function of time is d omega dt, which is 4. Now all we have to do is to plug in 0 for t, so the angular position at t equals 0 is just 5 radian The angular speed at t equals 0 is 10 radian per second. The angular acceleration at t equals 0 is 4. In other words, there's no time dependence here. The angular acceleration is a constant, and so regardless of what t value it is, the angular acceleration is always 4. Okay, next problem. And the last problem in this sequence of problems. A wheel rotates with a constant angular acceleration. Constant angular acceleration. Well, constant means that it's not going to vary. Angular acceleration is alpha, so they're telling us that alpha is 3.5 radians per second squared. The angular speed of the wheel at t equals 0 is 2 radian per second. So they're telling us that omega initial is 2 radians per second. What is the angular displacement at t equals 2 seconds? Angular displacement is, remember displacement is the change in the position, but the angular implies they want delta theta, okay? So the change in the angular position. Okay, well, delta theta, we have to use the kinematic equations for constant acceleration. And if we look at the equations that are available to us, we can readily obtain delta theta using the first one, delta theta equals omega initial t plus 1/2 alpha t squared, where t is none other than 2 seconds, right? Because at t equals 2 seconds. So 2 seconds here plus 1/2, 3.5 radian per second squared times 2 seconds, the whole thing squared. When we plug in our numbers, we should get 11 radian. Part B says, through how many revolutions has the wheel turned in this time? Well, we know how many radian have been described, but if they're asking us for revolution, we take the 11 radian and we do a unit conversion, because we know that 2 pi radian defines 1 revolution. So we want to know how many 2 pi's are in 11 radian. And the answer is 1.75 revolutions, because you can see here rad cancels, 11 over 1, 11 times 1 is 11, divide by 2 pi. The last part says, what is the angular speed at t equals 2 seconds? So they want omega final. And if we look at the equations we have available, omega final equals omega initial plus alpha t. That seems to be the most straightforward and reasonable. We make a substitution, 2 radian per second plus 3.5 radian per second squared times 2 seconds, and that gives us 9 radian per second. Well, this concludes the second part of the problem-solving session for Chapter 10. Until next